Hello there and welcome to a brand new lesson. This is How Beyond Numbers, where we learn maths the easy way. In this lesson, we actually want to prove the shoelace formula. We'll prove it, and then in our subsequent lessons, we'll actually work with it. So without much ado, let's quickly look into it. Now, talking of the shoelace formula, we are able to draw any polygon at all on the Cartesian plane, and we want to measure or calculate the area bounded within the polygon. It is the shoelace formula we use. To prove it, we are just going to use the decomposition of any polygon into trapezoids. Specifically, we'll be using the triangle. So without wasting much time, let's quickly look at the proof. Now, this is a note here, and you can pause and then read it. That is, if you so do wish. So we want to start by looking at this triangle over here. So as we can see, this is a triangle and it has three sides. This is edge 1, that is E1, then E2, H2, and then E3, H3. And for the points or the vertices of the triangle, we have P1, that is X1, Y1. Then we have P2, X2, Y2. Then we have P3, that is X3, Y3. Now, the green is the area that is bounded by the edges of this triangle. You see, and we want to actually calculate for it. Before we do that, if we take a trapezoid that is something like this, and we actually want the area of this portion, it is simply the average of the height times the width. Talking of the average of the height, that will simply mean, if you look at the y-axis, that is what represents the what? The height. So the coordinate of this one here is y1. Okay, so we have y1, then plus this height here is also what? Y2. That is, if you trace it all the way here, it is y2. So y2, then you divide it by what? 2, and then we multiply it by the width. So to get the width, this side is x2 and this side is what? X1. So x2 minus x1, that is the length of this width over here. You see, that will be the area of this trapezoid. This can be rewritten as 1 over 2, then into bracket you have your y1 plus y2, then in another bracket we have our x2 minus x1. Now, if you look at what we have here critically, you realize that if we take this point, so let me do that. If we move all the way from P1 all the way to P2, and then we bring it down to the x-axis, we're actually forming a trapezoid. You see, now this particular trapezoid we have here is the same as what we have over here. I'm going to prove that to you. So if I put it in here, you see it fits perfectly. Okay, so if we calculate the area of this particular trapezoid, and then we look at the edge E3. So for E3, that is to say, if I take P1 all the way down to P3, then I bring it down to the x-axis, you see I form another trapezoid. For this particular one, let me change the color to something else so that we can see clearly. So this is its color. If I'm to move it and then bring it all the way here, you see, and then if I'm to consider E2, you see E2, the edge E2, and we also form another trapezoid over there. So that is from P3 all the way to P2, and then we form this trapezoid. You see, now if I'm to pick this particular trapezoid, so let me first of all change its color. So let's change it to this color, you see, and then I move it all the way here. Now if you look at it carefully, what do you notice? You realize that the green portion we have left here which is actually the area bounded by the triangle, is what we have left over here. Do you see? Okay, so that is to tell you that if I'm able to find the area of the white trapezoid, that is the very big one, and then I find the area of this other one, that is this one, and then I find that of this as well, and I subtract it from the white one, the bigger white one, it is going to give me the area of this small triangle. That is what the proof is all about. Do you see? So let's take our time and then do it. So let's start by first of all solving for the area of the trapezium formed by E1. And by E1, I mean from this point all the way to this point, then coming down here. You see? So we want the area of this particular trapezium. That is going to be the first thing we want to do. So our area, that is of E1, is going to be what? We said for a trapezium, it is half or the average of the y's. So y1 plus y2. You see? Then the difference between the x, that is x2 minus x1. You see? So that is going to be the area of this particular trapezium. Then we come to the area of E2. So for E2, this is going to be the trapezium it has made. You see, because you see this is our E2, just as we proved. So we want the area of this particular trapezium. Okay. So for E2, we are going to say we have 1 over 2. So the same set of formulas. So we have 1 over 2, then into bracket, into y coordinates. The one here was x3, y3. So we have y2 plus y3, that is y2 and then y3, the heights. Then into bracket, x2 minus, this one is x3. You see, because x2 is ahead of x3, that is why we choose to do it this way. Then we now come for the area formed by E3. So for E3 as well, then we are going to say we have half of, that is y3 and y1. So y1 plus y3, then the difference between the x's. So x3 minus what? X1. So this is what we have now. So with all this done, let's try our very best to simplify these equations we have over here. Okay, so starting with the very first one, here's our first equation. So I'm coming to simplify it. Now we can move this 2 from here and then bring it to the left hand side as a coefficient. That is trying to what? Remove the fraction. So that we have 2, the area of E1 is equal to, so we now expand. E1 multiplies everything, Y1 multiplies everything we have in the bracket, then Y2 will also take its 10. So we have Y1 X2, that is in this direction. Then we go to Y1 times X1 as well. So we have negative Y1, then X1. Then we move in this direction as well. So we have positive y2 x2. Then finally, let's times this, which will then give us a negative x1 y2. So that is it for the first one. So for this second equation as well, that is from here, we are going to do the same thing. This 2 should come to the left hand side so that we have 2ae, that is the area of E2, which is equal to y2 times x2. We have y2 x2, then y2 times x3. We have a negative y2 x3. then y3 times x2 gives us a positive y3 x2, then y3 times x3 gives us a negative y3 x3. Then we look at the final one, that is that of E3. So for that of E3, the same procedure. 2 should come here so that we have 2. Then the area of E3 is equal to, we have y1 times x3, which is a y1 x3. Then y1 times x1, which gives us a negative y1 x1. Then plus y3 x3, that is when we multiply this, and then our last multiplication, that is a negative y3 x1. Now, following our initial proof that we did, that is with the diagrams, then it simply means if we want the area of the triangle bounded by E1, E2, and then E3, then it simply means the area of the trapezium of E1, so that is E1, right? We should take out, that is all of this plus all of this. We should add them together and then remove it from this whole trapezium. You see, that is what we did geometrically. So minus E, so that is the area with E1, then minus E2, and then what? The area of the trapezium E3. You see, so you should add E2 and E3 and then take it out of E1. Now, from the equations we have been able to come up with, then we have to add E2 to E3. Then the addition of this will give us 2 of E2 plus 2 of E, so area of E3. Then now we want to add these others as well. So if you look at y2 here, it has no counterpart here, but then if you look at y3x3, this is negative and this is a positive counterpart, so they would cancel out. Do you see? Now we observe and then check if there's any other thing to cancel out, and you realize that there's actually nothing to cancel out. So our 2ae2 plus 2ae3 is going to be the y2 x2, then minus y2 x3, then plus what we have, okay, then plus this one, so y3 x2, then plus what we have here, which is y1 x3, then minus y1 x1, then minus our last term, which is y3 x1. Now, if this is what we have, then it simply means for this formula we have this part of it, you see. So all we need to do now is to remove all of this from the area bounded by E1. So that is to say, if you want to negate all we have here, then we are going to negate everything here, so that we have negative of 2a of E2, then 2a of E3 is going to be equal to, so we are negating everything here. So negative y2 x2, then if we negate this negative, it becomes positive y2 x3, then negative y3 x2, then we have negative y1 x3, then we have positive y1 x1, then we have a positive y3 x1. I do hope you were able to follow. All we did was, this is a negative that affects everything here. Now, this is all that we have for this particular bracket. So if the negative is affecting it, then it simply means all the term we have should be negated. And if you are negating, it means if it is a positive, it becomes negative. it's a negative, it becomes positive in that order. So this that we have, we want to subtract it from the area bounded by E1. That is to say, the area bounded by E1 minus this is going to be equal to, so the area bounded by E1 was this over here. So all I'm going to do is I'm coming to copy it, this. Then since we already have these ones evaluated as what we have here, I'm just going to continue with it down here. So this is what we have, and we want to evaluate it. Now, if we observe, you realize that there are some opposites we can simply clean them off or cancel them away. For instance, if you take y1 x1, this is a negative y1 x1, this is also a positive y1 x1. So that can cancel out. Then we have y2 x2. There is also a negative y2 x2, so that also cancels out. And then finally we have, I think looking at it, we don't have any other term to cancel out. So these are what we have left of our evaluation. It simply means the difference between these two give us this. Now let's pay critical attention to what we have here. Now it is important to note that we had these two over here. So let's not forget to also write the 2's as well. So I can just remove this and then put my 2 over here. Now evaluating all of this, since we have 2 with all these, we can factorize the 2 outside. Then we have into bracket a of E1, then minus a of E2 plus a of E3. You see, and that is equal to. So for these as well, we can group them. Those that are positives can be written separately. So that we have y1 x2, that is, I've written this. Then there's also another positive, so plus y2 x3. So written this. Then we have this other positive, so plus y3 x1. Then we come to the negatives. So this is the first negative. So negative x1 y2, then another negative here. So negative y3 x2, then a negative y1 x3 as well. Now, if you remember this, we have here this particular one in the square bracket was actually the area of the triangle. You see, so we can simply say, not forgetting this 2. So 2, then this in this bracket being the area of the triangle is equal to. Now, if we want to preserve the order, we have y1 x2, then plus y2 x3, then plus y3 x1. So if you want this to also be arranged nicely, we can say minus, so we have x1 y2, then minus, let's write the x's first, so x2 y3, then minus x3 y1. So we can choose to factorize the negatives out, so that we have 2a being what, y1, that is to say all of this same thing, but then we bring a bracket here. Then factorizing this negative, we can then change all of this to positive. I do hope you are beginning to see something here. So with this, if you want to make A the subject, we have our A, being equal to, we are going to divide both sides by 1 over 2. So we divide by 1 over 2, and then we have what we have here, DC, then minus the next one as well. Now take note, we know that the area can never be what? Negative. So the formula can then be rewritten as A, which is the area, is equal to 1 over 2, then the absolute value over x1, y2 plus x2, y3, then plus x3, y1 minus, into bracket we have our y1, x2 plus y2, x3, then plus our y3, x1. That is all. This here is the Shoelace formula that is used to solve for what? The area bounded by a polygon. Now, it is shoelace because of how we derive it. So the simple way to derive it is this. For a set of points, let's take a triangle for instance. So if you have a triangle with points x1, y1, x2, y2, and then x3, y3. All we want to do is to write them vertically. So that you have your x1, then you have y1, then x2, y2, and then x3, y3. Then you end again with the first one here. That is x1, then y1. Then we do our multiplication. So this one here should multiply this. This should also multiply this. This should multiply this. So in the reverse order, y1 also multiplies x2, y2 multiplies this, and then this multiplies this. You see? So going back to the formula to see how this applies. You see, we have a half. So the half is constant. So our A is equal to 1 over 2, then the absolute value of x1 times y2. That is what you have here. So x1, y2 plus then x2, y3, x2, y3 plus x3, y1. So x3, y1. Then if you are going the reverse order, you subtract. So y1, y2, y1, x2. So y1, x2 plus y2, x3, y2, x3, and then plus your y3, x1, y3, x1. This is the Shoelace formula. So I do hope by the end of this lesson, you've been able to understand how this formula comes about geometrically, and you'll be able to explain to anyone as well. See you in our next lesson where we then apply this formula. Bye for now. And if this is your first time on this channel, you think it will be of help to you, you can choose to subscribe so that anytime I release a video, you'll be notified as well. See you in our next lesson, and bye for now. Do stay safe.